In this video, we're going to look at the atomic spectra. So this is going to be a bit of an intro to the following lessons, and it's going to contain some background information and some lead-in information to the types of emission spectrums that we're going to look at soon. The learning intentions are covered here, so the science theory is all around how a spectrum is created through particles, and then the learning intentions for today are to describe the changes in spectrum for a filament globe, describe the unique characteristics for the emission spectra of elements, and explain how the uniqueness of elements can be used to identify the presence of an element. To start off with, we'll look at the continuous spectrum. The electromagnetic spectrum, which we've covered extensively so far in this course, is outlined below, and in particular we see the visible spectrum down here. Linking back to particle theory from earlier years, solids, liquids and gases contain vibrating particles. The particles are continually vibrating as they always have some amount of energy. So unless we bring something to absolute zero Kelvin, the thing is going to be vibrating or having some sort of motion to it. The atoms rotate around their covalent ionic and metallic bonds, and as the temperature increases, the kinetic energy of that particle also increases. Here we can see at the top the continuous spectrum. So this is just the Roy G. Biv color spectrum. Below it we've got the emission spectrum, which we're going to see in this lesson, and in a later lesson we're going to look at what the absorption spectrum is and where that comes from. The particles within a material that are vibrating are protons and electrons, and these can vibrate at very different frequencies, which results in a different range of the electromagnetic spectrum emitted. As we've seen earlier, frequency or color is just the rate of vibration. So if the particles are vibrating at different amounts, different colors or different frequencies of the EM radiation spectrum are going to be produced. The range and intensity of the radiation that's emitted only depends on the temperature of the material itself. At room temperature, the radiation is very low for the average material, and it generally falls into the infrared range, which is our heat signature radiation. Here we can see some sort of spectrum of intensity versus wavelength. So here we can see as the intensity increases, we can see the wavelength here. So what this is this is a spectrum of light, and we can see that the curves are different temperature bands. So later on we're going to look at something about dominant frequencies, and we'll see why this is would be considered visible light because of the dominant frequency. But for now we can just see that at different temperatures we see different intensity and different frequency and wavelengths as a result. So if we consider a filament globe, so for many of you, you may not have even used one of these. They're kind of redundant now that the LED globes or even the energy efficient fluoro style globes are in date, but they use a thin tungsten wire that runs a high current through it, which generates so much heat in the filament that it illuminates, it gives off a lot of light, and that's what we use as an old style globe. So within this globe, as the filament is heated, those particles begin to vibrate more and more. The frequency of that vibration moves from the infrared into the visible spectrum, and that's why we see the yellowy white light that's given off. And as the blue/violet end of the visible spectrum starts to increase, the wire appears to glow white. The dominant frequency is the one with the greatest intensity and the one that's most seen or measured within a color spectrum. So we can see in this picture here, if this is our Roy G. Biv and the intensity is shown, we can see that at different temperatures here, we're more in our red-orange color. So that's why the lower temperatures we start to see reddy-orange. And as we get hotter and hotter, you can see that it's starting to spike across the color spectrum, and it's moving more towards that violety color. And if we start merging all of those color spectra, our eyes perceive it more as a white color. Earlier we saw the relationship lambda equals V on F, or V equals F lambda, that is the wave equation, where frequency is inversely proportional to wavelength. So therefore the hotter an object, the faster it vibrates, which is high frequency, hence the shorter the wavelength. The wavelength of the violet-blue light is smaller than the wavelength of the red-orange light. Therefore, as the temperature increases, there is a shift towards the blue/violet end of the visible spectrum for light, which is more blue, whereas for a cool filament, much more red and orange is dominant within the color. And you see this when we look at different types of globes, or even if you have those smart globes at home, you can choose between cool versus I don't know what they call it, warm I think they call it for white light. You'll notice that the cooler color is a little bit more orangey, and that's because of this. We're shifting into this red-orange dominant spectrum, versus your other one is more in the violet-blue frequency, so it has more of a pure white or a very subtle bluey tinge to it. So this is linked with the learning intention of describing the change in spectrum of a filament globe as the temperature increases, and that's what we've talked about in these last two slides. Now if we move on to the line emission spectra. When vapors of elements are heated, colors are going to be produced. And the colors are actually determined by the emission spectrum of the element. For example, neon actually produces orange light, whilst helium produces yellow, and mercury produces blue. A line emission spectrum is produced when the atoms of a pure gas are heated to high temperatures or subjected to a very large potential difference. These can only be generated in gases. We can't have it in solids. Only a gas can produce a line emission spectrum. One thing to note that we're about to see in some examples is that the emission spectrum produced is not continuous. So it's not like the filament globe we saw before. It has a whole range of frequencies from red all the way up to violet. In this case, the emission spectrum is very, very distinct frequency bands. For example, here we have an image of a hydrogen emission. We've seen this in class where we had a tube filled with hydrogen gas, and if we apply a very high potential, so something in the order of 5,000 volts across the tube, it actually excites or energizes the particles in the gas enough to start to give off light within a visible spectrum. If we then look at that through a spectrometer where it splits it into its bands, and this is what we did in class, we saw this picture. So we can see that there is a very bright red band, then we have complete darkness in between, then this sort of aquary color, then darkness, then blue, and so on and so forth. So this is unique to hydrogen, this pattern. Think of it as like its barcode. What we see is discrete lines instead of a continuous spectrum. So we can refer to them as distinct or unique, but we refer to them as discrete lines, which means that these frequencies are a property of the atom itself. They're not due to the vibration of charges. So it's a unique barcode for that atom. If that's the case, it means we can use the line emission spectrum to identify gases given the fact that they are unique. And we can see in this picture here, these are the barcodes or the emission spectra for certain gases, so hydrogen, sodium, helium, neon. And the cool thing about this is we can use them to identify other objects. If we know what hydrogen looks like and we know what sodium looks like, if we had a hydrogen-sodium gas mix that was excited or heated up, we could see it through the spectra and we could match it to our existing codes to figure out that it contains hydrogen and sodium. You may have done in previous years what we call the flame test, where you sprayed a metal solution through a Bunsen burner and it changed colors, and it looks something like what we see here. What you are actually seeing is part of that emission spectra of that metal or that material being vaporized into a sort of a gas form, and then as it's energized through the heat of the flame, it gives off a color spectrum that we can see, which is what we observe here. So how do we use that spectra? At a temperature of around 60,000 Kelvin, it starts to produce a range of frequencies that cross the infrared, the visible, and the ultraviolet regions of the EM spectrum. The dominant peak frequency is in the ultraviolet region at this temperature, and the object would appear more of a violety white color. An example of this is the star Rigel, which we can show below, that has this exact appearance. So if we use this information, we can look at the star, match it to this intensity frequency graph, and we can figure out that it's burning at about 60,000 Kelvin. So we can use that information to identify the gas composition as well, but also identify the temperature of a star without needing to ever go there. We do this in astronomy all the time. We often refer to warm and hot stars in astronomy as well, and this is identified by that emission spectrum and their visible appearance. An example of this would be that a warm or cooler star would appear more orange or more red, and a very hot star would actually appear more white, blue, or violet. And it links exactly to what we talked about earlier with that filament globe. As we're hotter, we burn more towards the end of the visible spectrum, so we've got more of that bluey tinge, which is also closer to what we see as white, whereas something that's a little bit cooler is more in the red, orange, yellow part, and we start to see that orangey color. So we can see some examples down here. Our sun is around 6,000 to 5,000 at the surface, and we see it as that yellowy color. If we go down to Arcturus or Antares, we see they're much cooler. We see yellowy to reddy color. And then as we go hotter, we start to see more of the white, and then if we go hotter again, we see more of that blue tinge star. Another example that you may have seen before is a very famous diagram called the Hertzsprung-Russell diagram. This is a very powerful diagram used in astronomy to show the life cycle of stars. And from this we can see a relationship between color, which is the dominant frequency in this case, and the temperature. And so what the Hertzsprung-Russell diagram does is it matches the luminosity of the star to the temperature, and we create what we call the main sequence. So this is where most of the stars start their lifetime. So they're created somewhere along the main sequence, and as they start to get older, depending on what they are, they either start to fade out and go into that brown dwarf sort of phase, and they get cooler as well as dimmer, or they could get brighter depending on the stage. If they start to go supernova or condense into like a neutron star, they get much, much hotter and much more bright. So this is something that if you continue physics at university, you may have the opportunity to deal more in. If you pick some of the astronomy classes, you do a lot of stuff on the Hertzsprung-Russell diagram, and it's really interesting to look at the astronomy aspect of this. So from here, have a go at the workbook questions. In the next lesson, we'll start to talk about these emission spectrum in a lot more detail about what is actually going on. But other than that, I'll see you next lesson.
I guess you guys aren't ready for that yet.
That was awkward.